Okay, hello guys, welcome to another video. I know this is not a legal contest video. In fact, I am not doing legal contest anymore because I will be grinding code forces. So far recently, I've just been up solving problems. But I will make videos for problems which I think are interesting and maybe a little bit educational for you guys. So here is one of them. It's called the longest special path. Now, if you look at the C-list rating, C-list is a website with all the major better programming platforms on it. So would you just search this? You can see it's 2700. That means it's quite difficult for most people, but um yeah. So I'll go over it, I think. Yeah. So to start with this problem, what you have to realize is here, let me actually draw the problem. I'm going to map a magical connection. So let's just say I have a tree like this, right? It's just a chain, and then it has some value. So let's say this is 5, this is 1, this is 5, 2, 2. So you can see some of the good paths are this one, because then you can't include both fives, right? And this one, and this one, even this one. So if you notice, like if you look at this chain, what you can do is you could go down. You can keep going down until you hit the character you've seen before, then you just exclude that. So the reason why I'm talking about this chain is you can map it to a very similar legal problem. Um, Let me find it. It's actually a very good problem, by the way. This one. So if you just reimagine these letters as some numbers, you reword the statement as longest substring without repeating numbers, then this problem is the same as this. So this longest special path, it's just this medium problem, but on a tree. And how would you solve this? Well, you just do sliding window. So you start with the first character, you go as far as you can, and if you counter the first character again, then you know the left boundary has to change to the one position after the last occurrence of that character. So then you be BCA, then you find this B, then you go to CAB, C, and then ABC, and so on and so forth. So this is just a two-pointer problem, and you can see if we have this chain, then we can just apply two-pointer, but we can't. That's the problem, because, well, you may have multiple neighbors, right? Like, I don't know, this is, make this 10. I'll make this 20. You can see, for example, let me give these some values too. This is 4 and this is 3. So if I am going along this path, let's just say I go to the 20, right? Everything so far is valid. Now, how do I go from here to here? Well, it's like I have to somehow efficiently go back up to 1, then down to 2. And then the same problems occur. Let's just say I go down. Let's just pretend this didn't exist. Now, how do I go from this node to this node, right? Because we have to consider all of the neighbors. Well, this is what people call sliding window on a tree. So, sliding window on a tree. Okay. So how do we do sliding window efficiently? Because we have to, in this case, go up from 4 all the way up to 1, then back down to 10, right? So what we're going to do is after we hit this 4, after we're at this 4, we're done with getting the answer ending at 4. We're going to reverse everything we did at 4. So basically, we're going to go back to 3. We're going to reverse everything we did on 3, going back up to 2. We're going to reverse everything we did back to 1, reverse everything we did, and then now we could go back to 10. So this is actually just this is just a DFS. So what we have to do is we have to do 1, update the data for the current node. And 2, we have to go through each neighbor of the current node. Then 3, undo what we did at step 1. So if I were to kind of demonstrate how this would run conceptually, so I will go down from 5 to 1 to 4. And then now we go back up to 1. So now we're at 0, 1, and 2. Well, we know we cannot have this 0, so we cut that off. And then we keep going down, right? Now, when we go back up, we know we cut off the 0 at node 2 because they have the same value. So since we're going back up, we're going to add back this node into whatever data we want to keep. So now it looks like this again. And then we go down to 3. We go down to 10, I mean. So that is conceptually what we want to do. Now, obviously, this problem, it wants a little bit more data in its answer. It wants, first of all, each edge has different lengths. And we also have to keep track of number of nodes. But those don't really matter because since we're performing sliding window, we're basically finding out for each node how many nodes up can we include. So we basically just maintain the answer for each node and just take the best one out of everything. So let me just go over what I kind of did. So I construct a graph. Now, I have to know where the last node of the same value is. So this tells me the all the nodes with same value visited from most to least recent. That's why I use a stack. So whatever I just put in a stack will be at the top. And then this is our prefix sum. Data of, so the first one is the length, and the second one is nodes. So back to this. So if I look at this path, well, I know the last node I visited with same value is this one. So then I can just do the sum of the weights. So per weight I add, well, I treated the length as a weight in this one, but I add a weight going to this node, I keep track of it. So W is sum of links from root to current node. And then this is number of nodes from root to current node. So then we can just do inclusion exclusion, right? So it's just number of nodes up to here minus number of nodes, including the last one. So that would be 2. And then for the weights, I did something a little bit cheeky because the way my DFS works is when you descend to a node, I add the edge to that. So, like for example, I need a better example. So if I'm considering this, let's just imagine this is a 2. Let me give these some values. So this is 5, this is 10, this is 11. So the sum of the weights above node 1 is 5. And then the sum of the weights up to node 3 is 26. There's this little weird gimmick I did where, because if we just do 26 minus 5, right, we will not give the right answer. We also want to exclude this 10. So what I did was a little cheeky trick where for each node I say I basically say what is the weight I use to go from this node down to its child. So I actually do that here. And I add it and then I subtract it away to keep the data consistent. But yeah. So overall, the big idea is sliding window on a tree, and then just maintaining data. So this is me updating the data for current node. And this is me reversing everything I did. Now let me talk about a special case. Let me write it down here. This is a case I encountered, which got me a wrong answer. So if we're at node 2, we know there is not a previous node with 5, with a value 5, but we do know that these two are the same, so we cannot include both of these. So actually, is it that test case? I forgot what the test case is. But anyways, there is something we have to do to we basically want to figure out the closest node that we cannot include. So it's not just the last occurrence of the node with the same value. I'm trying to come up with a counterexample. Well, actually, this is a sufficient counterexample. Well, let me change that back to 5. So don't be fooled when you're at node 3. You include everything because there's no previous node with value 3. You have to realize, well, so far we know we detected these two with the same value. So the closest node we cannot include is this. So you can do that with a stack. Well, I just did that with local variable that I can revert to after. So the way you check, so the way you maintain it is it's just the number of nodes, right? So if the last occurrence of this node, like the number of nodes up to it is greater, because the greater the number of nodes, that means that the deeper down the path it is, therefore closer to us, then just update it. But yeah, that's pretty much the problem. Sliding window on the tree, very good problem. So I will see if I will make any more legal videos. But yeah, see you guys.